I want to start with something that sounds like a limitation and turns out to be the whole point. There is a galaxy whose light has been traveling toward us for more than 12.5 billion years. When that light left, the universe was roughly 1.2 billion years old, less than a tenth of its current age. Galaxies were still being assembled out of the raw material left over from the Big Bang. By the time that light reaches the James Webb Space Telescope, after crossing most of the observable universe, it lands on the detector as a smudge, a faint patch a few pixels across. There is no structure in it that you can see with your eyes. You cannot pick out spiral arms or a bright core or anything that looks like a place. It is a blur, and inside that blur, astronomers have now found three supermassive black holes. Not three galaxies each with a black hole. One galaxy, containing three of them, all actively feeding at the same time. This has never been seen before anywhere in the distant universe. Two of those three sit so close together near the center that even Webb, the most powerful telescope ever built, cannot separate them into 2 points of light. They blur into one. Their separation is smaller than the smallest thing the instrument can resolve at that distance. And one of the two is eating faster than the standard theory of black hole growth says is possible. The galaxy is called J0148-4214. The paper describing it was published in the journal Astronomy and Astrophysics on the 12th of August, 2026, by a team led by Hannah Blair at the Max Planck Institute for Extraterrestrial Physics. Here is what I want you to stay for. First, if you cannot resolve two objects as separate points, how do you prove there are two of them? There is a technique for this, and it is genuinely one of the most elegant things in observational astronomy. Second, the phrase almost touching is doing an enormous amount of work in the coverage of this story, and the true number is both much larger than you expect and much more interesting. And third, the third black hole, the one out in the galaxy's outskirts, may have been thrown there. Violently, by something that happened before. Subscribe if you want more of these. Real papers, real data, and none of the exaggeration. Start with the problem this discovery is trying to solve, because everything follows from it. Almost every large galaxy has a supermassive black hole at its center. Ours does. It is called Sagittarius A star, and it weighs about 4 million times what our sun weighs. The question that has been sitting in astrophysics for decades is how these things got so heavy so quickly. Because when we look into the early universe, we do not find small black holes slowly growing. We find enormous ones, already in place, weighing millions or even billions of solar masses, at times when the universe was far too young to have built them by any gradual process we can write down. There are broadly two ways to make a black hole heavier. The first is to feed it. Gas falls in, the black hole gains mass. Simple in principle, but there is a brake on it, and the brake is important for what follows. As gas spirals into a black hole, it heats up and radiates. That radiation pushes outward on the gas still falling in. So the black hole's own brightness fights its own appetite. There is a point where the outward push balances the inward pull, and that point sets a maximum feeding rate. It is called the Eddington limit. Under normal circumstances, a black hole cannot exceed it, because if it tries, it blows away its own meal. The second route is to merge. Two galaxies collide, their central black holes sink toward each other, and eventually they combine into one heavier black hole. No feeding required, you just add them together. This route is attractive because it is fast, and speed is exactly what the early universe seems to demand. But it has been extremely hard to test, and the reason is embarrassingly practical. To confirm the merger route, you need to catch black holes in pairs. And to catch them in pairs, you need to tell two of them apart in a galaxy that is barely more than a smudge. For most of the history of astronomy, that was simply impossible. Which brings us to how you find a black hole you cannot see at all. You never see the black hole. That is worth saying plainly. Nobody has ever imaged a supermassive black hole in the distant universe, and nobody is going to. What you see is gas, and how that gas is moving. Close in around a feeding black hole there is a region where gas orbits at tremendous speed, pulled by an enormous concentrated mass, hundreds, sometimes thousands of kilometers per second. That gas glows, and hydrogen in it emits at a very specific wavelength. Now, because that gas is orbiting, some of it is coming towards you and some is going away. Light from the approaching side gets shifted slightly toward the blue. Light from the receding side gets shifted toward the red. Add it all together, and the emission line, which should be sharp and narrow, is smeared out into a broad hump. The width of that hump tells you how fast the gas is moving, and how fast the gas is moving tells you how much mass is packed inside its orbit. In this galaxy, the team measured hydrogen moving anywhere from a few hundred to nearly 3,000 kilometers per second. There is a second check they used, and it is what separates a real black hole detection from a false positive. Alongside hydrogen, galaxies emit light from oxygen in what are called forbidden lines. Those lines can only be produced in very thin gas, because in dense gas, the atoms collide too often for that particular emission to happen at all. So if you see broad hydrogen and no matching broadening in the oxygen, you know the fast gas is in a small, dense region, not a whole galaxy's worth of turbulence, a compact, deep gravitational well, a black hole. The team saw exactly that. But in the center of this galaxy, the shape of the hydrogen emission was wrong for a single source. It was lopsided, structured, complicated in a way that one black hole does not produce. The best explanation was two. And this is where they did the clever thing. The technique is called spectro-astrometry, and here is the idea. You already know you cannot resolve 2 points of light. That is a hard limit set by physics and the size of your telescope mirror. But you can do something else. You can ask, for each individual velocity in that broad smeared hump, where on the sky is the light at that velocity coming from? If there is one black hole, the answer is the same position for every velocity. Everything comes from one spot. If there are two black holes at slightly different positions, moving at slightly different speeds, then the light at one velocity comes from a marginally different place than the light at another. You are not resolving them into two dots. You are measuring the center of light shifting as you tune across the spectrum. That shift can be measured far more precisely than the resolution limit of the image. It is the difference between separating two streetlights at a distance, which needs a big lens, and noticing that the center of the glow moves when you look at different colors, which does not. Using this, they placed two black holes in the galactic center. Then they found a third out in the galaxy's outer region, far enough from the center to be picked out directly. They also did the work of ruling out the boring explanations. Supernovae can produce fast-moving gas. So can shocks, stellar winds, and very massive stars. Each of these leaves its own fingerprints elsewhere in the spectrum, and the team checked for them and did not find them. Now, the separation. The number I promised you. The two central black holes are about 620 light-years apart in projection. I want to be honest about what that means, because you will see this reported as two black holes almost touching. And that phrase will give you completely the wrong mental picture. 620 light-years is not close by any human standard. The nearest star to our sun is a little over 4 light-years away. So these two black holes are separated by roughly 150 times the distance from us to our nearest neighboring star. If you were sitting next to one of them, the other would not fill your sky. It would be somewhere out there among the stars, invisible. They are not touching. They are not nearly touching. So why is everyone excited? Because of a problem in astrophysics that has been unresolved for about 50 years, and it goes like this. When two galaxies merge, their black holes do not fall straight together. They sink slowly, and they sink by giving away energy to their surroundings. They plow through the sea of stars around them, gravitationally flinging individual stars away, and every star they throw out costs them a little orbital energy, so they drift a little closer. This works well, for a while, but as the pair tightens, they run out of stars to throw. They have already cleared out the ones on orbits that bring them close enough to interact. The supply dries up. At that point, roughly around 1 parsec of separation, which is a little over 3 light-years, the mechanism stalls. The thing that finally finishes the job is gravitational waves. Two massive objects orbiting each other radiate energy as ripples in space-time, and that carries away orbital energy until they spiral in and merge. But gravitational wave emission is extremely feeble until the objects are very close indeed. It does not take over meaningfully until they are around 100 times tighter than where the stars ran out. So there is a gap. One process stops working before the next one starts. And in that gap, in theory, pairs of supermassive black holes could stall for longer than the universe has existed. That is known as the final parsec problem. And it matters, because if pairs really do get stuck there, the merger route to building heavy black holes does not work. And we are back to explaining early monsters with feeding alone. Now, 620 light-years is about 190 parsecs. So this pair has not reached the difficult stage yet. They are still well above it. I want to be clear that this discovery does not solve the final parsec problem, and the researchers do not claim it does. What it does is show that pairs like this genuinely exist, this early, at separations this small, in the middle of a galaxy that is still assembling itself. The team's estimate is that these two will merge within the next few 100 million years. And the pair is strange in a way that is worth noticing. The two central black holes weigh about 80 million and about 600,000 solar masses. That is a wildly unequal pairing. One is more than 100 times heavier than the other, but it is the small one that is feeding hardest. The 80 million solar mass black hole is accreting relatively sedately. The 600,000 solar mass one is going at a rate that exceeds the Eddington limit, the theoretical ceiling I described earlier. It is eating faster than the simple theory says it should be able to. The whole galaxy contains about 1.3 billion solar masses of stars, and these black holes make up a meaningful fraction of that. In the nearby universe, a galaxy's black hole is typically a tiny fraction of a percent of its stellar mass. This is not that. This is a galaxy where the black holes have run ahead. Which brings me to the third one. The third black hole weighs around 2 million solar masses and sits about 5,500 light-years from the center, out in the galaxy's outskirts. And that position is a puzzle, because black holes are supposed to sink toward the middle. Gravity pulls them there, and dynamical friction keeps them going. Finding one parked in the suburbs needs an explanation. The team offers two possibilities. The gentle one is that it is on its way in. It arrived with a galaxy that merged into this one earlier, and it is still migrating toward the center. And we happen to be watching partway through. The other possibility is that it was thrown out there. Here is how that would work, and it is one of the more remarkable predictions in general relativity. When two black holes merge, they radiate gravitational waves. If the two are unequal in mass or spinning in different directions, that radiation does not come out evenly in all directions. More momentum leaves one way than the other. And because momentum is conserved, the newly merged black hole recoils in the opposite direction. It gets kicked by the asymmetry of its own gravitational wave emission. These kicks can reach hundreds or in extreme cases thousands of kilometers per second, which is fast enough to launch a supermassive black hole clean out of the center of its own galaxy, and sometimes out of the galaxy entirely. If that is what happened here, then this galaxy has already been through a black hole merger. The third object is the survivor of it, still coasting outward from the recoil, and the two in the middle are lining up to do the same thing again. That is one galaxy, at one point 2 billion years after the Big Bang, in the middle of its second black hole merger, still carrying the evidence of its first. There is one more thing that makes me trust this result more than a single paper usually warrants. In the same week, a completely separate team led by Haiwan Su at the International Gemini Observatory published a different result in Nature Astronomy. Using Webb together with the ALMA radio array in Chile, they confirmed a pair of feeding supermassive black holes in a merging galaxy, seen when the universe was about 1.3 billion years old, separated by roughly 4,900 light years. Different team, different object, different instruments, different journal, same conclusion, in the same 7 days. Black hole pairs in the early universe are not exotic accidents. They appear to be a normal part of how galaxies grew. Now the honest limits. Because they matter. Every separation quoted here is a projection. What we measure is the distance between these objects as they appear on the sky. The real three-dimensional distance could be larger because we have almost no way to tell how far apart they are along our line of sight. 620 light-years is a minimum, not a measurement. The two central black holes have not been imaged as two objects, and they never will be by this telescope. Their existence rests on modeling an asymmetric emission line and on tracking a subpixel shift in where the light is coming from. That is rigorous work, but it is an inference, not a photograph. The masses carry real uncertainty. Estimating a black hole's mass from the width of an emission line depends on assumptions about the geometry of gas you cannot see. And the recoil kick explanation for the third black hole is a possibility the team raises, not a conclusion they assert. It might just be falling inward. But here is the finding I keep coming back to, and it is not really about this galaxy at all. The team estimates that without spatially resolved spectroscopy, without the specific instrument mode that lets you take a separate spectrum at every point across the image, only one of these three black holes would have been detected. 1 out of 3. This galaxy had already been observed. It had already been cataloged as a galaxy with a single active black hole. The other two were sitting in data we already had, invisible because we were looking at the whole galaxy at once instead of point by point. So what did Webb actually find? 3 feeding supermassive black holes inside one galaxy in the early universe, 2 of them close enough that they will merge, one of them possibly the wreckage of a merger that already happened. In a system whose light left before the Earth existed, and before our sun existed, and before most of the elements in your body had been manufactured. And the uncomfortable part is the last one. If observing a known galaxy in a new mode turns one black hole into 3, then the census we have been building for decades is not a census. It is a lower bound. Every distant galaxy we have cataloged as having one active black hole was cataloged using the technique that found 1 out of 3 here. So I want to know your instinct. When we go back and re-examine these galaxies properly, how many of the black holes we think are single do you think will turn out to be pairs or triples? Tell me in the comments, because the honest answer from the people doing this work is that they do not know yet, and they expect to be surprised. If you want more of these, real papers, real data, and the parts where scientists say plainly what they do not know, subscribe. Next time, we are looking at what happens in the instant 2 of these finally touch. Thanks for watching.